So we're studying chapter 3, which is the subject of linear maps. So let's recall the definition. And most of what we do in linear algebra from now on is studying linear maps from one vector space to another. So we have vector spaces V and W. And we look at a function T from V to W. And such a function is a linear map if it satisfies the following two properties. First is additivity. For any vectors U and V, this is for all vectors U and V in the vector space V. T applied to the sum of U and V is T of U plus T of V. And the second property is what we might call homogeneity. For all vectors V and V, and all scalars lambda in the field F, T of lambda times V is lambda times T of V. And script L of UV, script L of VW, is the set of all linear maps T from V to W. And we saw many examples of linear maps. For example, the zero map. Zero applied to any vector V is the vector 0. Or the identity map. So the zero map is from any vector space to any other. And the identity map, I, from the vector space to itself, is just I of V equals V. It's the identity map. In calculus, differentiation is a linear map. And integration say the definite integral from 0 to 1 is from all that say continuous functions on 0, 1 into the reals. Integration is a linear map. But you learn in calculus that the derivative of the sum of two functions is the sum of the derivatives. The integral of the scalar times a function is the scalar times the derivative. The integral of the sum of two functions is the sum of the integrals, and so on. And there are many, 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 many important examples of linear maps all through mathematics. An important property of a linear map is it's completely determined. I mean, a vector space has infinitely many vectors, but a linear map is completely determined by a finite set of vectors that make up a basis. So suppose V is a vector space with a basis, say it's n-dimensional, n vectors, And let W be a vector space. And a set of vectors, not a basis, W1 up to Wn, then there exists a unique linear map T from V to W such that T of the basis vector V sub I gets sent to this arbitrary vector Wi for all I from 1 up to n. And the proof is the following. Let's call this set B. Since B is a basis, every vector B in V is some linear combination of vectors in the basis. And we define T of V, and that's going to be T of C1 V1 up to Cn Vn. If this is going to be linear, it's going to have to be C1 T of V1, C2 T of V2, up to Cn T of Vn. That's going to be C1 W1 plus C2 W2 up to Cn Wn. So if you define the vector, the linear map T from V to W by this formula, then you can check, we did last week, this is a linear map. And there's one and only one linear map that sends T of each basis vector Vi to W. Now, it's also always interesting that from vector spaces, you can construct new vector spaces. If you have functions S and T, which are linear maps from V to W, we can define the sum of these two functions, S plus T of V, to be S of V plus T of V. And we can define the scalar multiple of T by lambda of V to be lambda times T of V. And sorry, yeah, no, this is right. Lambda T of V is defined to be lambda times the vector T of V. So this is a way to add linear maps and to multiply a linear map by a scalar. And when you do that, you get new linear maps, and L of VW is itself a vector space. So this is very important. If you have a vector space V and a vector space W, the set of all linear maps from V to W is itself a vector space with these natural operations of addition and scalar multiplication. You can also, just the way you do in calculus, where we had composition of functions, suppose we have a linear map T from the vector space U to the vector space V, and a linear map S from the vector space V to the vector space W. So it's like here we have U, V, and W. We have this function T from U to V. We have a function S from V to W, and we can compose them. Get the function ST from U to W, defined by ST of a vector U is S of T of U. You take a vector U, it gets sent to some vector T of u, and then S sends that to S of T of u. So this is composition or the product of linear maps. Any questions about this? So finally, one last property of a linear map. So this is, we might call it Theorem 311. This is in section 311. You have T, a linear map from V to W. So in V, we have the zero vector in V, and in W, we have the zero vector in W. These are different vector spaces. Each vector space has a zero vector, but they're not, but they're different vectors, so they're in different vector spaces. So if T is a linear map, then it always sends 0 to 0. T of the zero vector in V gets mapped to the zero vector in W. And the proof is the following, namely 0 plus 0 equals 0. So if you take the zero vector in V and you add it to itself, you get 0. So T of the zero vector, that's T of 0 plus 0. But because T is linear, this is T of 0 plus T of 0. Subtract T of 0. You get T of the zero vector minus T of the zero vector. It's T of the zero vector plus the zero vector minus T of the zero vector. So here I have two vectors in W. I'm subtracting the vector from itself, and that's the zero vector in W. So this is T of the zero vector in V plus the zero vector in W, and the zero vector has the properties, the identity. You add 0 to any vector, and you just get back that vector. So this is T of 0. So this is a proof. This last thing. Any questions about this? Okay, so this was a review of section 3A, and the topic for today is section 3B, which is on the null space of a vector space of a linear map and the range of a linear map. So today we're going to learn what these two objects are and prove a fundamental theorem about linear maps. So suppose we have a linear map from a vector space V to W. So T is in the vector space of linear maps from V to W. And the null space of T, which is also called the kernel of T. So here we have V, here we have W. We know that the zero vector in V gets sent to the zero vector in W, but there can be other vectors that get sent to 0. So the null space of T is all the vectors B and V such that T of V is 0. Everything that gets sent to 0. So for example, suppose we had B and W equal to R2. And we have the linear map T of xy equals x minus y y minus x. For example, if I took the vector 3, 7, T of 3, 7 would be 3 minus 7, 7 minus 3. That's the vector minus 4, 4. This is a linear map from R2 to R2. And the null space of T, if all the vectors x, y, the T of x, y is the 0 vector. That's all vectors x, y, such that T of x, y, what is that? X minus y, y minus x equals 0. That's all vectors x, y, where x minus y is 0, where x equals y. Or instead of all vectors x comma x, it's an r. X comma x is just x times the vector 1 comma 1. So here's R2. The vector 1, 1 is right there. And this XX, this is this line. This is the line y equals x in R2. So for this linear map from R2 to itself, the null space is a set of all vectors on this line through the origin. So let me just pause for a minute so you have a chance to review the definition of the null space and to convince yourself or ask me to explain why for this linear map, the null space is this one-dimensional subspace in R2. Any questions about this? All these are new concepts, new definitions, and they require a fair amount of study. Let's look at another example. Suppose my vector space is all functions f from R to R that are differentiable. They're all functions that you can differentiate. And my linear operator D in this vector space from V to itself is D of f is the derivative. Actually, suppose I take f to be V to be not all functions. It's just all polynomials. That's P of R. All polynomials, none. And D of F is the derivative. So you know if you have a polynomial, F equals, I don't know, 7x to the 9th minus 3x to the 5th plus 21x minus 7. The derivative is 63x to the 8th minus 15x to the 4th plus 21, right? This is differentiation. So the null space is all functions, all polynomials f, whose derivative is 0. What functions have derivative 0? It's just all the constant polynomials, constants. Make the polynomial f of x equals 7, the derivative is 0. And the only polynomials whose derivatives are 0 are the constants. So the null space for this linear map is just a set of constant polynomials. And the important thing right away about the null space is, so this is a theorem, you have a linear map T from V to W. This is theorem 314. The null space is always a subspace of the vector space V. So again, we have V and W, and the map T from V to W, a linear map. The 0 vector gets sent to 0, but of course, you can have a larger subspace, a larger set of vectors that get sent to 0. So this is in red, the null space of T. So all the vectors that get sent to 0. And this assertion is the null space is a subspace. So prove, first of all, we let null of T be the null space. So 0, the 0 vector is in the null space because we proved T of 0 is 0. And if U and V are in the null space, then T of U plus V, this is linear, so this is T of U plus T of V. But if U and V are in the null space, T of U is 0, T of V is 0. 0 plus 0 is 0. That's good. So if U or V in the null space, U plus V is in the null space. And if I take the vector V and multiply it by a scalar lambda, T of lambda times V is lambda times T of V. That's lambda times the 0 vector. And a scalar multiple of the 0 vector is the 0 vector. So lambda V is in the null space. So the null space is a set of vectors that contain 0. It's closed under vector addition and scalar multiplication. That's the definition of a subspace. Any questions about this? Now, there's an important property, two important properties of any function, of being one-to-one or injective and being onto or surjective. So this is the definition of injective. A function t from v to w is called injective or one-to-one. If, well, again, let's draw a picture. If you take two different vectors, v and u, v gets sent to t of v, u gets sent to t of u. If v different from w, or if u different from v, then v implies t of u is different from t of v in w. So functions one-to-one are injective if you take two different vectors in v, they get sent to two different vectors in w. It cannot be that two different vectors get sent to the same vector. So that's injective or one-to-one. And Theorem 316 says that you have a linear map T from V to W. T is injective if and only if the null space of T, which is a subspace, consists just of the zero vector. So the proof is simple once you understand it, and maybe it's hard until you understand it. So suppose T is injective, let V be in the null space of T. Then T of V is zero. But also T of zero is zero. So if this T is injective, if V gets sent to zero and zero gets sent to zero, then V equals zero. But you can't have two different vectors getting mapped to the same vector in W. So the only vector in the null space of T is zero. So that's the proof going from left to right. If T is injective, then the null space is zero. So now, let's suppose the null space of T is zero. Let U and V be in the vector space V. If T of U equals T of V, then T of U minus V, because T is linear, this is T of U minus T of V. But these are equal, so this is zero. So that means U minus V is mapped to zero. It's in the null space of T. But the null space of T only has one vector and it's zero. So that means U minus V equals zero, or U equals V, which means T is injective. So a linear map is injective if and only if its null space is zero. Questions about this? Now, this is V and this is W, and T is a linear map from V to W. We know that 0 gets sent to 0. And we know that there might be a larger subspace of V that gets sent to 0. But we also have everything in V gets mapped into W. So there's some set of elements in W that contains T of V for every V in V. And that's called the range. So the range of T is the set of all vectors in W of the form T of V. So you take a vector in V, it gets sent to some vector T of V over in W. So all those vectors in W, which are the images of a vector in V, that constitutes the range of T. So for example, suppose I take P2 of R to be the set of all polynomials of degree at most 2. This is all polynomials, ax squared plus bx plus c, for any real numbers a, b, and c. And define D from this vector space to itself by differentiation. So D of a vector ax squared plus bx plus c, when I differentiate, I get 2ax plus b. So this is a polynomial of degree at most 1. And if I take any polynomial of degree at most 1, and I look at the quadratic function a over 2x squared plus bx, for example, b of this function is ax plus b. So when I differentiate a quadratic polynomial, I get a linear polynomial. And every linear polynomial is a derivative of some quadratic. So if I look at this function differentiation from quadratic polynomials to quadratic polynomials, the range of D is the set of all linear polynomials. It's a proper subset of the set of quadratic polynomials. So just this fact from elementary calculus that the derivative of a quadratic polynomial is a linear polynomial allows us to say exactly what is the range of this differentiation function in this example. So in this example, what you see is I had this vector space of quadratic polynomials in this linear map from the space to itself of differentiation. And sitting inside the space of quadratic polynomials are the linear polynomials. And everything in this vector space is mapped into this. So there's lots of stuff over here which is not in the image or in the range. So in this case, the range of D is not equal to this whole set. It's a subset of it. It's the derivative of a quadratic is linear. But it sometimes happens that the range of a linear map is the whole space. So for example, if you look at P of R to be all polynomials of any degree, the map D from P of R to P of R, well, it covers everything over here because every polynomial is the derivative of some other polynomial. If you have a polynomial of degree n, it's always the derivative of a polynomial of degree n plus 1. And we say that a linear map T from V to W is onto if the range of T is not a subspace subset of W, it's all of W. So onto or surjective. Those are the two words that are synonyms. And I should say one more theorem, prove one more theorem. This is Theorem 319. If T is any linear map from a vector space V to a vector space W, the range of T is a subspace of W. So the proof is as follows. We have to show that the range of T is closed under vector addition and scalar multiplication. So that W1, W2 be in the range of T. So what this means is there exist vectors V1 and V2 and V such that T of V1 is W1 and T of V2 is W2. But then this means that the sum of the vectors W1 plus W2, that's T of V1 plus T of V2, but T is linear. So this is T of V1 plus V2, and V1 plus V2, this is a vector in V. So T of V1 plus V2, which is W1 plus W2, is in the range of T. So the range of T is closed under vector addition. And similarly, lambda times W1, that's lambda times T of V1. But because T is linear and homogeneous, this means this is T of lambda V1. But lambda V1 is just another vector in V. So lambda W1 is also in the range of T. The range of T is also closed under scalar multiplication. And finally, just state the obvious, 0, which is the image of the 0 vector, in the range of T. So the range of T is a non-empty subset of W that contains 0. And it's closed under vector addition and scalar multiplication. And therefore, it's a subspace. So in most subjects, there's something so important. It's called a fundamental theorem. So in calculus, you learn the fundamental theorem of calculus. In linear algebra, there is the fundamental theorem of linear maps. So The picture is the following. We have V and W, and T is a linear map from V to W. So sitting over in V, we have the kernel of T, or sorry, the null space of T. Sitting over in W, we have the range of T. And the theorem says that if V is finite dimensional, if V is a finite dimensional vector space, then the range of T is also finite dimensional. That means it has a finite basis, or it can be spanned by a finite number of vectors. And the dimension of V is the dimension of the null space of the linear map plus the dimension of the range of the linear map. So this is a beautiful statement. It's 100% certain that on the midterm or the final, you're going to be asked to prove this theorem. If it is, the fundamental theorem of linear maps. So the proof, I'll just show the proof that's given in the book. So we know that the null space of T is a subspace of the vector space V, and the subspace of a finite dimensional vector space is finite dimensional. So suppose the dimension of the null space of T is M, and let's suppose that the dimension of this larger vector space V that contains the null space is N. So if the null space has dimension M, that means there's a basis U1 up to U sub M in the null space of T, which is a basis in the null space of T. And we proved in any vector space, every linearly independent subset can be extended to a basis. So actually, just to follow the notation, the dimension of V is going to be M plus M. So, so there exist vectors V1 up to Vn in V such that U1 up to U sub M together with V1 up to V sub N is a basis for V. And we must show that the range of T is finite dimensional and has dimension equal to N. So let's proceed to do that. So again, here we have V inside of V, we have the null space of T. So U1 up to UM is the basis for the null space of T, U1 up to UM, followed by V1 up to Vm, is the basis for the whole vector space V. So if I take any vector in V, there exist scalars A1 up to AM and B sub 1 up to B sub n, such that the vector V, this is a basis, so every vector is a linear combination of these n plus n vectors. V is A1 U1 up to AM U sub m plus B1 V1 up to B sub n V sub n. But then T of V is T of A1 U1 up to AM UM plus B1 V1 up to B sub n B sub n. And because T is linear, this is A1 T of U1, AM T of UM, V1 T of V1, Vn T of Vn. But U1 up to UM are in the null space of T. So these vectors are all zero. So this is all zero. So T of V is just equal to this. T of V is V1 T of V1 up to B sub n T of Vn, which means that the list of vectors T of V1 up to T of Vn spans the range of T. Over in W, where you have the range of T, every vector is a linear combination of these n vectors. These are not necessarily linearly independent, but they certainly span the range of T. So the dimension of the range of T is finite. It's in fact, it's in most n, less than infinity. So the range of T is finite dimensional. And in fact, what I want to show is that the range of T is in fact equal to it. And the way I will do that so we know that T of V1 up to T of Vn, these vectors span the range of T. And I have to prove T of V1 up to T of Vn are linearly independent. Well, how can we prove that? Suppose we have some linear combination C1 T of V1 up to C sub n T of Vn equal to 0. Because T is linear, this is the same as saying T of the vector C1 V1 up to Cn Vn, T of that vector is 0. That means this vector C1 V1, C2 V2, and so forth up to Cn Vn is in the null space of T. But remember, U1 up to UM is the basis for the null space of T. So that means that there exist scalars D1 up to Dm such that C1 V1 up to Cn Vn equals D1 U1 up to Dm Um. Another way of saying that is that C1 V1 up to Cn Vn minus D1 U1 minus Dm Um is 0. But these vectors, the v's and the u's together, are linearly independent. So the only linear combination of them equal to 0 is, so linear independence implies all the CI's and all the DJ's are equal to 0. So in particular, V1 up to Vn are linear, T of V1 up to T of Vn are linear. So the dimension of the range of T is equal to. So that is, in fact, the complete proof of the fundamental theorem. But to understand it, you have to go back to the book, look at the proof, and word by word, line by line, go through it to make sure you can understand what's going on. It really is a completely, these are one of the most fundamental theorems in linear algebra, but it takes some time to think about it to understand. The dimension of the null space plus the dimension of the range equals the dimension of the domain V. That's the fundamental thing. And I'm going to give 3 examples, corollaries of this fundamental theorem. Let me state the fundamental theorem again. I have T from V to W. The dimension of V is finite dimensional, is the dimension of the null space of T plus the dimension of the range of T. So corollary 323 says the following: if V and W are finite dimensional, and V has a larger dimension than W, then for all linear maps T from V to W, T is not injective. And the proof is as follows. We have the dimension of V. It's the dimension of the null space of T plus the dimension of the range of T. But remember, the range of T is a subspace of W. So the dimension of the range of T is less than or equal to the dimension of W, because the subspace cannot have larger dimension than that of the ambient space. So this says the dimension of V is the dimension of the null space of T is less than or equal to x, we'll make this bigger, less than or equal to the dimension of the null space of T plus the dimension of W, which means the dimension of the null space of T is greater than or equal, just bring this over to the other side, dimension of V minus dimension of W. But our hypothesis was that the dimension of V is strictly bigger than the dimension of W. This is greater than or equal to 1. So the null space is not 0. But the 0 space is 0 dimensional. So T is not projective. You map three-dimensional space into a two-dimensional space by a linear map. It cannot be one-to-one. Any questions about this? The dual statement is if you map a linear space into a higher dimensional space, it cannot be surjective. So we have, again, a linear map T from V to W. If the dimension of V is less than the dimension of W, then T is not surjective. And again, the proof is the fundamental theorem. The dimension of V is the dimension of the null space of T plus the dimension of the range of T. So, and the dimension of the null space of T, whatever it is, 0, 1, 2, 3, this is greater than or equal to the, it gets smaller if I throw this away, dimension of the range of T. So another way of saying this is this, we write it. Dimension of the range of T is less than or equal to the dimension of V, but the dimension of V is strictly less than the dimension of W. So here I have W. Sitting inside of it is the range of T. This subspace has dimensions strictly smaller than the dimension of W. So the range of T can't be equal to W. So T is not surjective. Now, linear algebra derives from studying linear equations. And the basic problem in high school algebra for 1 or 2 or maybe at most 3 variables is solving a system of linear equations. And suppose you have a system, so here's the equation, summation k goes from 1 up to n, a sub 1 k x sub k. What does this mean? This is a11 x1, a12 x2, up to a1k xk. That's a linear equation equal to 0. We have another linear equation, a2k xk. So this is a21 x1 plus a22 x2 plus a2k xk equals 0. Let's say you have, up to n. These are equations of n variables. And let's say you have m equations. So what we have here is a system of m equations, linear equations, in n variables, and it's homogeneous. That means the right-hand side is all zero. And we want to find all solutions of this system of equations. This is just what you did in high school algebra. You might solve, high school algebra, you have things like, 2x plus 5y equals 0, 3x minus 2y equals 0, find all solutions. So that's two equations and two unknowns. Here, we have more equations and more unknowns, but it's still a linear system. We have m equations in n variables. And we want to find all solutions. Now, obviously, one solution is letting all the x's equal to 0. So the question is whether there is some non-zero solution. You can think of this as a vector space equation where there's an associated linear map. So you can define T from Rn to Rm by T of x1 up to xn, that vector is the vector summation a1k xk, k goes from 1 up to n, summation k goes from 1 up to n, a2k xk, up to summation k goes from 1 up to n, amk xk. So for every vector in n space, we get some vector in m space. And this is a linear map from Rn to Rn. And the null space of T is the set of all solutions of the homogeneous linear of the system, homogeneous linear equations we just looked at. Here was a system of linear equations, and a solution of that corresponds to a vector in Rn, which is in the null space of T. And the system has a non-zero solution if and only if the null space of T is not just 0. So I proved a moment ago, if T is a linear map from V to W, and the dimension of V is greater than the dimension of W, then T is not injective. So here I have T from Rn to Rm. If n, which is the dimension of Rn, is bigger than m, which is the dimension of Rn, then T is not injective. What does this mean for our linear equations? If we have n variables, m equations, and n is bigger than m, then that then is a non-zero solution. So this is just, in a sense, a fancy theorem from high school algebra, but it's very useful and very important. You have a system of linear equations homogeneous system and more variables than equations, the system always has a non-zero solution. Okay. So keep in mind, we have one more section according to the syllabus that I will do on Monday of next week. And the following Monday is the first midterm exam. So I will be sending out a review sheet, and Wednesday of next week, I'll be going over the review. So the first midterm is scheduled for Wednesday, March 2nd. No, sorry, that's not right. Today's the 23rd. You go over matrices, and Monday, March 2nd is the review, and then March 7th is the first exam. So just a tad under 2 weeks from today. So keep that in mind as you do your work, as you study. And really take advantage of my office hours on Zoom. If no one shows up, I close out the Zoom and go do some other work. But if there are questions, I'll generally stay on as long as there are questions. Any questions about any of this? Okay, that is it for today. Again, I remind you, I have an office hour early this afternoon and Thursday and Friday. Yeah, midterm March 7th. It's on the syllabus that's on Blackboard also.
Thank you, Professor. Have a great day.
Thank you. Okay. Bye all. Nice day out today. Enjoy it.